What's really important with relativity is to work out what frame of reference we're in at each point in time. So we've been asked how long the time would be for astronauts to travel a distance, but the distance that we're given, the 4.2 light years, which is, a light year is the distance that light travels in one Earth year, but that's measured from the frame of reference of someone on Earth. So we're always going to do our summary step first. So here's Earth, there's Australia, okay, here's Proxima Centauri. Well, we know that this measured from someone on Earth is 4.2 light years. Now we could calculate how many metres that is, we could calculate how many metres per second 0.5 c is, but actually it's a whole lot easier if we just keep everything in units of fractions of the speed of light. So this is going to be 0.75 c. We're going to use c as our units, and we're going to keep distances in light years, and therefore time is going to be measured in Earth years as well. Okay, so that's the distance measured by an earthbound observer. They both agree upon the relative velocity, but what we're being asked is how long would it take someone in the spacecraft, the astronauts themselves? Well, they're moving relative, and so they're going to see that length contracted. And so we need to work out how much is that length going to be contracted. So there's our summary step. Now we're going to pick our law. We're going to work out the length contraction here. So that's very simple. LV equals L naught, which is going to be 4.2 times, and here's our factor here, 1 minus 0.75 squared over 1, okay, which you can see how easy it becomes if we do everything in the units of the speed of light. Okay, so let's pull up something to help us actually do this calculation here, and it's always good to make sure that you don't do too much rounding off in relativity. Don't try to minimise your rounding off, because you're squaring a number and then you're subtracting numbers that are very close to each other. So the round off error makes a whole lot of difference. Okay, so we said it's 4.2 light years is the L naught from the observer's point of view, and we want to take that times the square root of 1 minus 0.75 squared divided by 1. Of course, that's just going to give us that. So now our length is going to be equal to, where did that little thing just go then? It's 2.778 light years. Okay, so if my distance is 2.778 light years, speed is distance on time, so my speed is my distance divided by my time. Therefore, my time is going to be equal to distance divided by speed, which is really simply 2.778 light years divided by 0.75 times the speed of light. So we're going to go that divided by 0.75 times the speed of light, and so it's going to take, the time is going to take 3.7 years. Now that's a bit strange, because it seems like we're travelling faster than the speed of light. If it's 4.2 light years, that's 4.2 years at the speed of light to get there. How is it only going to take 3.7 years from the point of view of the astronauts? Is there a conflict here? Is there a contradiction? Well, first of all, the astronauts are going to see that length contracted, so it's actually not going to be that far away at all. Secondly is the earthbound observers will agree that the astronauts thought it only took them 3.7 years, but they're going to say, yeah, but you measured that 3.7 years on your clocks, and your clocks were running slow. So there's no contradiction, everyone's happy, everyone agrees. The people on Earth see that it's going to take them actually quite a bit longer than 3.7 years, in fact longer than 4.2 years to get there, but they're going to agree that the astronauts thought it only took them 3.7 because they're going to see their clock running slow. So everything works, everything's mirrorable. Of course, the other way we could have tackled this question was to use the length, the time dilation formula, and that would have worked as well.